Hi, I'm Ben Canning, and this lecture is on digital communication. I know we went through this in class the other day, but I just wanted to repeat this and go through it with a little bit better slides. Just FYI, this was put together kind of rushed because I had to leave, so forgive me if things aren't as polished as they could be. Alright, so yesterday we talked about this idea of a process of converting a analog signal into a digital signal and what's required for transmission. You're going to need to know the purpose of each of these blocks, so the sample and hold, the clock, the analog to digital converter, parallel to serial converter, modulator, as well as on the other end for the receiving end. We'll go through that right now, just so that I can clear up anything that maybe was misrepresented yesterday. You don't need to be able to draw the inner workings of any of these things. You just need to be able to describe a block diagram like this, so kind of a functional diagram. One other thing to note is that you need to know that bit rate equals bits per sample. So that means if we take a single sample and it has 8 bits to it, times the sampling frequency gives you how many bits per second. Since this is bits per sample, this is samples per second, that gives us bits per second, or bit rate. In other words, like megabits per second, or megabytes per second, although you'd have to convert from bits to bytes in that case. Okay, so let's start off with this signal that I've drawn here for us. It's a little bit more complicated than the one we were working with yesterday, but we're going to start with the sample and hold process. So the sample and hold process is this idea that your device will be taking a small chunk of whatever analog signal is coming in, holding on to that, and meanwhile, while the rest of the signal is coming in, holding on to that next chunk of the signal. And then it's going to proceed to convert this analog signal into a digital signal. So the sample and hold part would just be it's sampled. This is one chunk of a larger signal, and we're holding on to it. And then in the conversion process, we're going to be actually taking measurements from along this line right here. So, for example, if our sample rate is 1 million hertz, then the time between samples is going to be 10 to the negative 6th seconds, or 1 microsecond. That basically means that if the sample rate was actually 1 million hertz, that every microsecond we would be taking a new value as to what the analog signal was as it came in. So let's go through that process. One thing to note is that we're going to probably set a threshold as opposed to rounding as humans normally do. So humans normally round up or down at the 5 marker for any place value. While you can set a computer or digital device to do that, sometimes it's easier to just set thresholds, meaning that would be equivalent to rounding down to the nearest whole number. So for example, over here at a time of 0 microseconds, because notice this scale is in microseconds, so at a time of 0 microseconds, we're above 10 but below 11, so it's about 10.5. That would be rounded down to 10. At 1, it's at 13. That would be rounded to 13 still. At 2, it's at 14.0 approximately. That would still be rounded to 14. But at 3, it's at about 14.5. That would still be rounded down to 14. So we can notice how this process loses some of the precision and accuracy of the data. Alright, so your computer or device would do all these measurements, and if we follow along, so you can actually go through and look at this if you want, but you can see that these are the different signal values, meaning the actual value and voltage of whatever this line is at that point, and then I've converted those into binary code for us already. So this would be the binary code for 10, this would be the binary code for 13, the binary code for 14. I apologize if there are any errors, but just look at the general process, not the nitty-gritty details. Alright, so if you're confused so far, then pause, go back, and rewatch that bit, because we're going to move on. So at this point, this is kind of the analog to digital conversion portion, where we've gone from an analog signal, we've sampled it and held it for a brief period of time, converted that into a digital code, or a binary code in this case, and then we'll work with the actual transmission process and the other things. We're going to switch gears a little bit. I'm going to use a different representation, so it'll be similar, but we'll go a little bit different. So here we're now getting to the serial or parallel to serial converter. Now, what I mean by that is we took a sample back here and we were able to make a bunch of different measurements all at once. Well, we can't send all of those different measurements out at the same time. So we're going to need to go from 4 parallel measurements, and there would be more obviously, but we'd have 4 different parallel measurements, and we need to put those in one long chain to send out in a continuous stream as opposed to trying to send out 4 things at once. So that's what the parallel to serial converter does. For another example of that, or a more visual example, if we are sampling and holding our rainbow over here, we code in a few different values, the different colors. The analog to digital converter takes them from kind of continuous values to very discrete values. And whoa, that actually does a check mark. And then the parallel to serial converter takes our 4 discrete numbers or 4 discrete values that we've taken and sends them in one long chain so that we can send it out as a continuous message. Now, although this seems like it would take a long time, this process is actually fairly fast, to the point that although it takes an additional second, let's say after you take a 10-second sample, the time it takes to do all the conversion and send it out is much less than the data rate at which things are coming in. So this is where we start to free up a little bit of time to do other calculations and other things, and we'll get back to that later. But anyway, at this point, we've sampled our rainbow. We've put that into an analog to digital converter. That's given us discrete values, and then we've put that into a parallel to serial converter, and so that is keeping these things in one long chain. Now, that parallel to serial converter then sends things to a modulator. Well, the modulator just adds in a carrier wave and combines our data from the parallel to serial converter onto the carrier wave so that we can actually send it out. That passes it off to a transmitter, and the transmitter actually sends that. So here we've got these kind of waveforms of what we were originally thinking of. So that leaves us to the other end. On the other end of things, we have the signal coming in to a receiver. The receiver is basically just there to receive the signal. It's the antenna. We have a demodulator. I'm guessing you can guess what that does. It separates our carrier waves from the signal wave. Then we have a series to parallel converter, so maybe all of that data was for one single image of the rainbow. We want that all to come up on our screen at the same time. So that takes that long continuous string of data and converts it into a single packet of data again. And then the digital to analog converter just does the opposite, so converts our binary back into our analog signal. So this would be going from our coded 1s and 0s back into a, hey, this pixel should be blue, this pixel should be green, etc., and then finally pumps it out as a useful output. Now, if this is a radio or something similar, we might also have a few other things in here, which are amplifiers. The purpose of the radio frequency amplifier would be the radio signal coming in might be kind of weak. We might be really far away from the radio tower or things like that. So the radio frequency or RF amplifier would boost up that signal. So it would just zoom in on it or make it bigger, basically just amplify it. And then we have the audio frequency amplifier. So this is all still kind of in the inner workings of the device. The audio frequency amplifier would be the amplifier that would like convert our headphone level of output into large speaker level of output. So meaning going from the idea of only producing a little bit of sound, which might be what comes out of here, to adding in an amplifier that can now power huge speakers or lots of sound coming out. And so that's what the audio frequency amplifier is. Don't confuse those. One is dealing with the radio signal coming in. The other is dealing with what would actually be coming out of sound, or in terms of sound in that sense. All right, the last thing I want to talk about is I said that this whole process actually frees up some time. So while it can't happen at the exact same time, we do have to sample and hold and deal with things chunk by chunk. The whole processing takes a lot less than the chunk size that we are sampling. So what that means is we can start to send multiple signals at the same time. So here the A, B, and C represents, let's say, 3 different rainbow images that we want to send. Or maybe it's the rainbow image, and then the B signal is the sound we want to play with it, and the C signal is the subtitles. So we can actually begin to, we have enough space, like there's some downtime, some lag time, so we have enough space that we can send 3 signals at once. Now, the way they do this is they just alternate. So they would send a signal from, or they would send the A signal, then they would send a bit from the B signal, then they would send a bit from the C signal, and then they would start again from the A signal, the B signal, and the C signal. Now, from each of those, there are multiple bytes and codes and things being sent, but we can see how we can stagger these, and this is called time division multiplexing, and we can send multiple signals at the same time. Alright, that's it for this one. There are other ways to multiplex. We can use frequency multiplexing, and there are more complicated things than that as we get to more and more complicated radio signals. But that's it for now. Thanks.